Linear functions are mathematical relationships where the rate of change between two variables remains the same across the entire graph. This means that for every unit increase in the independent variable, the dependent variable increases or decreases by a fixed amount. The slope of the line, which represents this rate of change, does not vary at different points. It is constant throughout. Unlike curves, which have slopes that change from point to point, straight lines have identical slopes everywhere. The y-intercept only shows where the line crosses the vertical axis and does not affect the rate of change. This unique feature makes linear functions models of constant change. A quadratic function models situations where change happens in a curved, parabolic pattern rather than at a constant or exponential rate. Its graph rises and falls symmetrically, often representing motion affected by gravity. For example, when a ball is thrown upward, its height increases to a maximum point and then decreases as it comes down, forming a parabola. In contrast, fuel cost increases linearly with distance, salary remains mostly constant or linear, and bacteria growth follows an exponential pattern. Only the ball's height versus time shows the classic quadratic relationship, with the square of time determining its path due to gravitational acceleration. In the quadratic function f of x equals ax2 plus bx plus c, the coefficient a plays a key role in shaping the graph. Specifically, the sign of a determines the overall direction in which the parabola opens. If a is positive, the parabola opens upward, creating a U-shape, and the vertex becomes the minimum point of the graph. If a is negative, the parabola opens downward, forming an inverted U-shape, and the vertex becomes the maximum point. This feature is independent of the values of b and c, which influence the axis of symmetry and vertical placement. When a parabola opens upward, it means the coefficient of the squared term a is positive. In this case, the graph is U-shaped, curving upwards. Such a curve has a single lowest point, called the vertex, which represents the minimum value of the function. In real life, this can model situations like the shape of a bowl or the path of water collected in a dish. No matter how values change on either side, the curve will always dip down to a bottom point and then rise again. This behavior shows that the function decreases until it reaches the minimum, then increases afterward. The profit function given is quadratic. P of x equals minus 2x squared plus 40x plus 100. In quadratic functions, the coefficient of x2, called a, determines whether the parabola opens upward or downward. If a of 0, the graph is U-shaped and has a minimum point. If a is 0, the graph is an inverted U-shape, meaning it opens downward and has a maximum point. Here, since a equals minus 2, which is negative, the curve opens downward. This tells us that the company's profit will increase up to a certain level, the vertex, but cannot grow indefinitely. Instead, it reaches a maximum profit point. Turning points in the graph of a polynomial function occur where the curve changes direction, either from rising to falling or from falling to rising. In real life, these points often represent situations where a process or trend reaches a peak or a low before reversing. For example, in business, a turning point might show the maximum profit before it begins to decrease, or in physics, the highest point reached by a ball before it starts descending. They do not mean breaks or undefined values, nor do they show constant rates or random changes. Instead, they highlight meaningful changes in direction within a continuous trend. The degree of a polynomial function refers to the highest power of the variable x. This degree strongly influences the overall shape and complexity of the graph. For example, a first-degree polynomial, x squared 1, produces a straight line, while a second-degree polynomial, x squared, produces a parabola. Higher-degree polynomials, such as cubic x squared or quartic x4, create graphs with more bends or turning points, resulting in increasingly complex curves. The degree also affects the possible number of roots and the end behavior of the graph. It is not limited to shifting the graph or changing only the intercept, but determines the graph's fundamental shape. This question asks you to identify which real-life situation can be represented by a trigonometric function. Trigonometric functions, such as sine and cosine, are used to model periodic or repeating patterns that occur in cycles. They describe behaviors that rise and fall in regular intervals, just like waves. Let's consider the options. Profit increasing steadily is linear, not periodic. Taxi ride cost increases with distance, which is linear with a fixed start. Bacterial growth doubling is exponential, not cyclic. On the other hand, a pendulum swings back and forth in a repeating motion over time, showing oscillation, which matches a trigonometric function. The period of a trigonometric function refers to the length of the interval on the x-axis over which the function completes one full cycle and then starts repeating the same pattern again. For example, the sine and cosine functions repeat their wave-like graphs every 2pi units, meaning that after 2pi, the graph looks exactly the same as it did at the beginning. This repetition is a key property of periodic functions, which makes them useful in modeling cycles like sound waves, tides, and seasons. The period is not about slope, constant change, or maximum values, but specifically about the repeating interval of the function's graph. The question describes a student measuring ocean tides at a beach throughout the day. Tides naturally rise and fall in a repeating cycle caused by the gravitational pull of the moon and sun. This motion is not straight like a linear function, nor does it form a single curve like a quadratic. Polynomial functions can model certain curves, but they do not repeat in a predictable cycle. The key feature of tides is periodicity. The pattern repeats regularly over time, similar to waves. Trigonometric functions, such as sine and cosine, are designed to represent oscillations and periodic behavior, making them the most appropriate choice for modeling tidal patterns.
We share
tutorial questions and answers.
It is all about understanding facts and sharing with others.
Learning continues. We are learning to know, understand, and share with others.
Please subscribe to our channel if you like our videos.